Hello everyone, my name is Idalina Bonham, and today I'm excited to talk to you about enthalpy. I'll explain what it is, what variables are involved, and how we can model real data using enthalpy. Let's get started. Firstly, what is enthalpy? Enthalpy, symbolized by the letter H, is defined as the total energy of a thermodynamic system. It combines the system's internal energy, which includes things like the kinetic and potential energies of molecules, with the energy needed to displace its surroundings by pushing against external pressure. In simpler terms, you can think of enthalpy as the heat constant of a system when pressure is constant, which is usually the case in open-air environments or laboratory settings. In chemical reactions, enthalpy is crucial because it helps us predict how much heat will be absorbed or released when a reaction occurs. This tells us whether a reaction feels hot or cold to the touch, or whether it's endothermic or exothermic. Several important variables are associated with enthalpy: H, which is enthalpy itself; Q, the heat exchange with the surroundings; P, the pressure of the system; and delta H, which represents the change in enthalpy between the initial and final states. When a process occurs at constant pressure, the heat absorbed or released, Qp, is equal to the change in enthalpy, delta H. This leads to the important relationship delta H equals Qp, where Qp stands for the heat flow at constant pressure. Positive values of delta H indicate that the system absorbed heat. These are endothermic reactions. Negative values of delta H means the system released heat. These are exothermic reactions. We can model and measure enthalpy changes in the real world using a device called a calorimeter. A calorimeter allows us to measure temperature changes that occur during chemical or physical processes. One common method is coffee cup calorimetry, where the reaction happens in an insulated cup under constant pressure. For more precise measurements, we use bomb calorimetry, where reactions occur in a grid sealed container at constant volume. The key data we gather includes the mass of the substance involved, the specific heat capacity of the material, and the temperature change during the reaction. We then use the equation Q equals m times C times delta T, where m is the mass in grams, C is the specific heat capacity, and delta T is the change in temperature. Since at constant pressure, Q equals delta H, this allows us to calculate the change in enthalpy directly. When we plot this data, typically temperature versus time, we expect a roughly straight line trend during the main part of the reaction, representing a constant rate of heat transfer. In an ideal system, this trend line would be straight. However, in real-world conditions, slight deviations can occur due to heat loss to surroundings or imperfect insulation. For exothermic reaction, the trend line slopes downward as a system releases heat. For endothermic reactions, the trend line slopes upward as a system absorbs heat. So in summary, enthalpy measures the total heat content of a system at constant pressure. It's a powerful tool that helps us understand the heat flow in chemical reactions. By measuring temperature changes carefully, we can model real systems and predict whether reactions release or absorb energy. Thanks for watching, and good luck with all your chemistry adventures.